It's going to be Brian Kyanjo. Brian Kyanjo is working on a GeoFlood modeling for computational model for overland flooding. He's a PhD student here. I think he's in 4th year. So Brian, you have the floor. So, hi everyone. My name is Brian Kyanjo. Fourth year PhD computing student, and I'm gonna take you through my dissertation work, which I'm going to present in SIAM, 4th biennial meeting. So I'm gonna talk about GeoFlood. GeoFlood is a computational model of overland flooding. This is the code we have been working on for 3.5 years now. So I'll give you the details as we go on. So I'll start with the description of the code. So basically, GeoFlood is an adaptive distributed file software that basically incorporates forest record. Forest record is an atmospheric code that solves hyperbolic PDEs on logical Cartesian grids, and then it uses pforest for grid management. So GeoFlood is, because of the use of pforest and forest core, it has the low cutoff capabilities for non-rectangular domains that enables it to do several kinds of problems, i.e. those on cubic sphere. It has the core tree adaptive meshing because of the pforest. For Cartesian grid layout, you can do IJK when modeling problems, and because of the adaptive mesh framework, you can be able to get high resolution mesh adaptation and fine grain simulation capabilities. So this is how the code is laid out. So this is the major code, GeoFlood. It uses forest core and pforest as libraries for time stepping, dynamic grid management, and then the Riemann solvers that solve the shallow water equations are in here in the GeoFlood. So these are the extensions. It has the CP version and the CUDA version. So CP is just written in MPI, and then the CUDA version, we are just trying to accelerate these Riemann solvers to be capable of using GPUs. So you can access it on GitHub. It's ready available, at least the CPU version. The CUDA version is still under development. So during the process of developing GeoFlood code, we had to benchmark it. So during the benchmark, we have to compare it with already existing codes like Geoco and Heckel. Geoco is also based on a Clopper code. It's actually a submodule inside there has been developed by George, the University of Washington, currently maintained by the same Clopper team, and it's based on the WPA with propagation algorithm. So how does this compare with Geoco? Because we took some of the Riemann solvers from Geoco to incorporate them in GeoFlood, but the difference is the adaptive mesh refinement, which you'll understand in a bit. So this one is all the adaptive mesh refinement tasks are parallelized. The other ones are only serial. Chooses the batch, the block-based adaptive mesh refinement, the other one is structured. So the difference between the block-based is like this, the grid hierarchy here is stored as non-overlapping fixed grid sizes, stored as this and forest. While here it's just overlapping grids stored as nested grids. So both GeoFlood can run both on distributed and shared memory. This is only distributed on shared memory. That's because of the use of OpenMPI that can only use threads you can only find shared memory platforms. This has both OpenMPI and MPI during the parallelization in the CPU code version. So we maintain it with the CMake views. That one is the view system, just the make system. So those are some of the major differences between the two codes. However, both of them use the same Riemann solvers, as we got the Riemann solvers from that code to incorporate it in this, but just use a different MR strategy. So we also have HECRES. HECRES is a standard industrial code that is used for modeling like bridges, embankments, breaching, and all this kind of stuff. So it's based on implicit finite flowing method to solve the shower water equations on uniformly structured grids. So it's not adaptive at all. It's also capable of modeling stuff like dam breaks, rainfall, and all these kind of overland flows. So we are using it because it has already been benchmarked and has been proven to be a standard code for solving such problems. So GeoFlood is based on numerical methods. So these numerical methods are simply the shower water equations, nonlinear, which we call the depth average shower water equations, and we use the wave propagation algorithm designed by Levesque to solve these shower water equations. So the solution of a cell on a grid is approximated by Q, where Q is just a state variable consisting of height, momentum in Y and momentum in X, because it's a two-dimensional quantity. And then this is just a good enough type that wave propagation algorithm that updates the solution of each cell, depending on the time steps. So the augmented Riemann solver that we borrowed from GeoFlood is basically employs this kind of characteristics in wave the F-wave formulation approach. This one is just to take advantage of the source term. And this is good for rapidly changing bathymetry. As you know, there can be a flood, we have hills, mountains, flat areas. This is really good for predicting such flows. The road solver to provide exact solutions for single shock Riemann solvers, and also the HL type approximate Riemann solvers. So these ones, they provide a natural fix by providing like two waves, which are a good approximation for problems with large wave functions. So because of these three, this code is able to handle like presence of dry states, whether initially or during the time of the simulation. So we also use the AMR in protocol, which already explained the block structure. Basically, it looks like this. So this is a hierarchy of different patches at different levels, and a solution after adaptive mesh refinement simply looks like that. You can see the small boxes, big, small, small, small. That's what we call adaptive mesh refinement. So the refinement criteria designed in GeoFlood is basically, it helps us to tab refinement only if this kind of situations are satisfied. For example, we need the water on the surface, so that H has to be positive. We don't have to refine here lake region because we already have water there. We need to refine the magnitude of velocity after it being greater than a certain threshold, and we have to refine the, for example, the dam, so that we're able to track the solution along the path of the floodplain. So the flow gauges, this is actually a new one, a new criteria, which is based on predefined heights of momentum thresholds that you can design and say if the height of the flow is above this, don't refine. It is below this, refine everywhere. So during the benchmarking, the problems we used had hydrograph. This is not common in overland flow problems because modeling problems in flow hydrograph is hard, but actually that's what takes place. So to deal with this, we use what we call the Riemann invariance. It says that if you have a solution at the boundary, the solution inside and the solution outside, they all lie in the same curve. So solving this, we're able to get this equation that represents the inflow. So this is the inflow, like the inflow water. So this is for the test one, test two. These are how hydrographs look like. So this inflow is represented by pi. I am an shown because it's on the ghost side, and B is that's the channel width. You see how this looks like. So because of we already start out right, because as you can see, starts out no water, and then at the central point we get water. So we must have an actual entropy fix for cases where the height of the water is greater than the height of the water in the first cell in the domain. which gives us what we call a two-shock solution for the right-going waves. So these are some of the benchmark results. So what our fastest case is the filling depression. This accesses the ability of the code to predict endotension or low momentum flow over complex topology. As you can see, this is our topology just situated at a certain angle with 16 different depressions. If you look at it accelerated here, you can see the depression down here. So this is where we are simulating on. So we inject water at this point and we want to see how fast it grows down here and how efficient it does. So this is the comparison between HECRES and GeoFlood. So this is at T0. After 1 hour, you see, but their solutions are uniform. Our solutions are adaptive. I don't know if you see the grids adapting. But looking at the solutions, you can see that you're almost doing the same thing, which proves that the code is doing the same thing. And this is evident on the curves on, you can see, this is just a small GeoFlood gift to show what happens during the simulation. So this is also evident on the curves. As you can see, you're comparing GeoFlood, GeoCore, and HECRES. And GeoFlood is the one in red, and you can see that it's taking the same path at different depression mechanisms. And it is proving to be performing better than GeoCore, just because of we are handling the refinement criteria and the adaptiveness refining in certain regions. So the second benchmark problem seems to be obvious, but this is where we needed most, because we can be able to grow transect, because this is just a floodplain, just with some small inlet, as you can see. So this is the river here. You have a blockage, and then water has to flow out like that. So this is a good test case because you can draw transects in the middle diagonal to show how the different numerical methods are implemented and how that affects the both models. So as you can see here, the solutions still agree for the different models. And this is the most important thing, where we are comparing one-on-one HECRES and GeoFlood, and this is the transect just drawn just in the domain, the center of the domain vertically, and this is what happens if you have the transect diagonal from the center of the domain. So you can see that the solutions are different at T after 1 hour, and if we hold rate constant and vary the solution for GeoFlood after 1.5 hours, you can see that solutions are almost coinciding, which simply means that this HECRES is just faster than GeoFlood, but they're actually doing the same thing, which best proves that we are actually doing something there, which is correct.
So HECRES basically running the simulation faster.
Yeah,
getting away faster than GeoFlood. Why is that?
So this is when we are looking at a solution at an angle. Yeah, so the angle of attack is affected by the friction. So we are implementing the friction different. Yeah, the friction term. Because we are just, the formula is the same. We are all using the Manning coefficient, a G, and then the V over R2/3. So for them, they're using the hydraulic radius, which is the weighted parameter. Which is the weighted area over the weighted perimeter, which is something like B plus 2H. And for us in GeoFlood, GeoCore, we are using the same that we're just using the depth.
Okay, so different parameterization for friction.
Yeah, the different implementation of friction.
And if you would implement the same way, would you get the same result?
We have not tried out that, but we just tried out holding this constant and trying to vary GeoFlood at the next time step, and we almost got the same solution, and we are thinking that could be the reason.
Okay, but if you go back to one slide, you show there is this solution, right?
Yes.
One more second. There you go. So mathematically, forget the method right now. Right? This should be a semicircle no matter what, right? How the water progresses, and you're saying that so you're saying that if you cut this along X direction, you're gonna get a match, but if you cut it diagonally, you get difference. Therefore, one.
Cut here, we get the same. If you cut here, it's different.
So which code is wrong then? Because like one of them will not get the perfect circle, right?
Now the both get the perfect circle. It's just that this is faster than this one. So we are thinking that the solution of this one finally meets that one, but just at a later time.
I think these are looking down on it, and the other ones are a cross section.
I agree, yeah, that's exactly my point. Because then when you show that on one direction you match, and on the other you don't.
Yeah, because the impact of friction here is different to the impact of friction when you're looking at the flow at a certain angle.
Yeah.
I took that as looking at the cross section, at any given time, one model is gonna show the wave front at a certain depth. Where the other one, it might not have caught up to it, so it might be a different depth. So that makes sense. There's just a difference in depths, right?
Yeah, I'm just wondering why if it's symmetric, then why one direction than the other?
Yeah.
That's my question. Okay, but move on, I guess. And what if you go shorten those plots again, I wonder what are the axes exactly?
Okay.
This one, yeah. This is distance.
Yeah, it's distance, again, it's depth.
There's a profile of that thing, right? Yeah, same, no.
Perhaps angular invariant. It was the same.
Yeah, so looking at those plots, the one on the left, one in the middle, right? That's what Zach is saying. Apparently at time equal 1 hour, the propagation along X direction is both 400 meters, right? On the front of the wave, right? And the middle plot, propagation of high grass is still 400 meters, so it's symmetric. And your GeoFlood is not, it's shorter. So it looks like in one direction is going fast and diagonally is not going fast. So you shouldn't get a symmetric result that you just showed us. So that might kind of cognitive, problem here. I don't see the same thing on both slides.
Okay.
You see what I mean?
Yeah, I see what you mean.
So those look like two different results on two different. I feel like something is off, but maybe we can talk after.
So this is the third benchmark problem. So this was just to verify that we're able to simulate the transcritical flow of hydraulic jumps and waves behind this obstacle. So this is HECRES and this is the GeoFlood solution. And this is just the architecture of how the problem was designed. Yeah. So again, looking at the plots, we see that we are still getting the same, we're following the same trend as HECRES, which somehow tells us that we are doing the correct thing. So we had also to test the code on a real life problem. So this is the Mauperset downgrade problem that happened in France in 1959 after the collapse of the dam due to accumulating water that's accumulated to fill the reservoir after long-term rainfall that weakened the dam that was already weakened due to the mismatch in the during the construction. So we use the initial and boundary conditions to be assuming 0 sea level, and we set the initial reservoir, assume that we had 100 meters above the sea level. So using a Manning coefficient of 0.3, we can see that we're able to simulate the Mauperset downgrade problem, and this is the solution overlaid on the Earth surface. And you can see how the water displays down near the Mediterranean Sea, which was evident and similar to the event report. So these are the adaptive mesh requirement solution at t = 0 after 200 seconds and after seconds, and you can see how the code is adaptively refining as what I put down. This is the comparison at different gauges that was placed around the flood region. So these are the police survey points. They, according to literature, they said these were placed outside, not at the edges of the flood, and the gauge numbers were placed at the middle of the flood. So this for different models and compared with the system data, you can see that GeoFlood is still within the range. So this is where the adaptive mesh block structure solution is well explained to see what happens during the adaptive mesh refinement. So according to the results I showed previously, we use the mean level of 1 and a max level of 4, this is the typo. So the Mediterranean Sea is already having water, so we didn't want to refine here. So this was refined at 100-meter resolution. Then the dam was refined at the max level, which is 5 at 6-meter resolution. So what happens at level 1, we have one patch, one quadrant, I call it a quadrant. Then at level 2, this will be partition subdivided into 4 non-overlapping quadrants. So look at it the same way. This is how it will become. And then at the next level, this small one will be subdivided into 4. And then at the next level, this will be subdivided into 4. But these are all non-overlapping. Yeah. So when you're designing code, you also have to care about the performance and the scaling of the code. So looking at the performance tests, we can see that running the code with 32 processors, you can see that at some point, after like 8 processors, we can see GeoFlood trying to take over GeoFlood, which we assume that if we parallelize GeoFlood Riemann solvers, we'll be able to achieve a better performance right there. And this is evidence in the power efficiency. So to show that we are doing the same thing, this is the comparison table to show that we're using the same max level, different mean level, because GeoFlood starts at 1, GeoFlood starts at 0 when we are refining, but we made sure that whatever settings we have here, we are still using the same effective resolution, which is 2048. Yeah. So for the current work, we are trying to accelerate the Riemann solvers in GeoFlood using CUDA. And we have already done this in the Forest Core GPU code. And these are some of the results showing how CUDA overlaps CPU. And we're going to use some of those code in our next work. So what we are doing currently right now, we are trying to rewrite the Riemann solvers into CUDA, and this is how the structure is to utilize the Forest Core for the CUDA code. So we have to assign CUDA threads at each read interface to be able to parallelize the code. And the results we expect the same results as the CPU version, but we also expect like 15x speed up depending on the GPUs that we shall use and improved coefficients. Yeah, thank you.
Yeah, that was a good presentation. So on your second slide, you mentioned something like forest flow. I think it was a diagram. Yeah, I would really like to know how GeoFlood is working in conjunction with forest flow. All you mentioned is that it's a library, but your statement wasn't clear.
Okay. So what we use forest flow in, we use forest flow in GeoFlood as a library. So we use it to, so forest flow is a PDE layer on top of PForest which forest could use SP forest to do its grid management, to be able to do adaptive mesh refinement. So what we do in GeoFlood, we tap into, we put some files from forest core to be able to do our grid refinement. To solve also in the shovel acre. Yeah, that's the only time we use forest. The run routines, interpolation, and everything is right here.
Just a typo.
Data?
Typo.
Yeah. No, this is okay.
It's a food or flood?
Oh. I thought you were saying do that.
My other question lies on the accuracy on, so you made a comparison, right, of GeoFlood and like the other known softwares, but also I'd like to really know how the accuracy of GeoFlood compares with the other softwares, the well-known ones like the HEPAS and the other. Is it HEPAS? Yeah.
Yeah, so we haven't really tested the accuracy. The only point we are trying to say is that we can be able to predict the flood extent as those other flood models are doing.
There was also a flood that wasn't clear. You mentioned it was faster. What did you give me your mind?
That Hector was faster.
Yeah. I think I understood that for being more accurate.
You mean here?
Yeah, you did mention you said one of them was very fast.
Yeah, so we think that Hector's is, so if you look at the velocity, plots here. So we think like Hector's, the water flow is faster than that of GeoFlood and GeoFlood.
What do you mean by the water flow is faster? Like it, because these are models, right? I mean, these are software, so they're not really controlling the flow of water. So I don't get that from you.
So just looking at the solution here, you can see that if you look at all the circumference of this is not the same as this looks to be larger than this. The same as that. The same as if you look at the dam break problem, you can see that it's at 1 minute, but the flow is already here, the flow is not here.
So follow up on this. Clearly one is wrong, right? Like they're not the same, so one must be wrong.
At least.
At least one, right? How would you evaluate that? Like, why is the difference between them? And you told me the drag coefficient, the drag parameterization, right?
And the way they are implementing their shower water equations is different from the way we are doing.
But still my thinking is this: take a physical phenomenon, translate it into the shallow water equation. So you solve the equation, however, the results should be the same within certain small tolerance, depending on random errors, numerical methods and stuff, right? But if your errors are massively different, then something is wrong, right?
Yeah, that's true.
So I wonder if you say the difference is due to the friction force, what would happen if you remove that friction force? How would they compare then? You try.
No, I've not tried that. I've not tried to switch off friction. But the other difference is like we are using inflow boundary conditions that we are implementing totally different, because Hector doesn't disclose how they implement their inflow hydrograph boundary conditions.
That would change everything if you don't know exactly what's the initial condition or the boundary condition, right?
Yeah, so they don't disclose. So we don't know if we are doing it right or they're doing it right.
Basically, so then you don't compare. Yeah, okay. See.
So that's why we are just looking at, are we capturing the same flood extent? Then actually doing the same thing.
Your point. Okay.
Yeah.
That's okay. That's important information that you should say, because, you know, it's changing everything, right? Because those kind of problems, they are heavily sensitive to the, as you very well know, the initial condition, right?
Yeah.
It's really, the game is about tuning the initial condition of the method itself.
Does this benchmark come from some source?
Yeah, yeah. So these are UK benchmark programs that were designed to to show the accuracy of the existing flood models.
And did they not provide a reference solution or is it?
So they provide different solutions, but they again say that this is not actually the best solution because they don't have the exact solution, the analytic solution for these problems. They just made up them and they were considering like 8 different models and they were all performing different. And they were just only looking at how
Somebody did
Yeah,
take
sit
a
down,
tank of water and try it and see what happens.
It's actually not that simple. I mean, good idea, but it's, yeah.
You don't want to model somebody else's model, you want to model actually water. I'm not criticizing you, but somebody who makes up a benchmark should
You'll be surprised like
get a
how
tank of water and.
prominent this kind of approach is in those kind of fields. It's not, they're not all mathematicians, the people who work on that, unfortunately. But yeah, sometimes you feel like comparing, you know, apples to bananas, that's fine, right?
But to get at your point, if you're, across, they're offering this as a benchmark. So that's what its purpose is. It seems remarkable that they're not disclosing how they're, using their initial conditions. So you said they didn't disclose that, how they're implementing their initial sort of boundary conditions.
Yeah, so like if you look on literature, there is no straight way people implement boundary conditions.
Because presumably they're expecting whoever's taking them up on their offer to use it as a benchmark is going to be implementing some boundary conditions and that. You know, it wasn't the same because. No, I mean, is that common in a benchmark to not have all
No.
the information like that? It
No.
just seems remarkable.
No, I don't like that at all, because of course you shouldn't have all the data for a benchmark. However, and that's an opportunity too, to create one, right? And spec exactly how this is done, and you know, and then people can compare against you and not against Tegres, because it makes no sense, as you just showed us. That being said, it's very common to compare models which do things very differently, and still do it from the perspective of, let's see how different results we're gonna get, what the spread of difference, right? And people do that sometimes.
Okay.
Yeah, well, right. So I have to introduce you. Okay, so for the interest of time, yeah, just say, they're going to invite, Yao to. Is the topic. No, it's not. Oh, it's not okay. Should be there by now, right? Huh. Oh, I should share. You stop sharing? Yes. Okay. No, where it is. Okay, for the interest of time, I'll invite Gahounzo, student for Kopera, to come and talk about bioclinics splitting for layered shower water using the DG method. Thank you. Thank you, Brian. Yeah. So my presentation, this is part of my PhD research, and I'm working on operational modeling development. And today's presentation will be on 3 different things. We start with talking about the layered shallow water equation and multi-layered shallow water equations. Talking about the barotropic and the baroclinical splitting, how do we actually split those system of equations and solve them separately. And then talk about that's the numerical method we are using to solve them. And this has been done with my advisor, Mr. Kopera, and Robert from Horizon State University as my collaborator. And this, I'm start with giving some ideas of ocean model equation. So I look at this equation with hydrological model. And this one has some assumption where we assume that the density is constant, except when you want to consider some buoyancy term. And that approximation is called a boost next approximation. And the second one of the set of equation used to develop model is the hydrostatic model, where we assume the hydrostatic assumption, when the gradient pressure, the gradient of the pressure is equal to the density of the gravity. And in this case, we assume that we have different crucial layers of water. And the last one is the shallow water models, and that's commonly used in when I want to model economies of flooding, like my previous speaker said. And these have a different application. For instance, you want to simulate a very small feature in the ocean or the dynamical feature, you can use the hydrological model. But if you consider large scale simulations, you have to go for hydrological one and then this one. So tsunami modeling, you go for the shallow water equations. But my work is mainly on this second one because we are developing model of the entire ocean. So we need something that can result in large scale simulation of features. So multi-layer ocean, what does that mean? That just means that we consider an ocean. Let's put an ocean in ocean, sorry. So we have ocean with different layers, and each layer of this have a different density, and those densities are constant. And each layer has its own velocity, its own height. And then the surface of the ocean will have the wind blowing and some external forces. We assume that it's constant, and we assume that each layer has a constant density, its own velocity, and also own height. But as the time goes on, when the simulation goes on, we know that each layer interacts with each other, creating some additional forces of what we call the stress. And we ought to account that when we are building this model. So each layer is described by particular set of dynamical equations. And what are those equations? So let us say we have so many layers and we just want to look at it from the cave layer in that system. And that layer is these two equations. The first one is the conservation of the mass equation, and then the second one is the momentum equation. And we have a different terms in this equation. And those who are familiar with shallow water equation, this one is a bit different, but if you just consider one single layer of the equation, you can work on this and go back to the original shallow water equation we all know. So we have this representing the equation and all the rest, and also most importantly, we have this term and this term as well that creates add those external forces like wind, the bottom stress, and also the stress due to the interaction between the layers. So we have this equation. We can just decide to put some numeric on this and solve it, but unfortunately, it doesn't work that way because if we just go ahead and solve this, we have some issues, the stability issues, and also the performance issues. So we have to solve this differently. So that's why we come to the second one, which is the biotropic and biochemical splitting. So the idea is we know that in the ocean we have different features that vary at different time scales. So that's you have the fastest motion in the ocean, the external gravity wave due to the gravity waves. And then the presence of those gravity waves impose a severe restriction to how far we can go in time, like the times that we need for the model to run. So those pose then it's better to now split the previous equation into extract the fastest motion and model them with different equation, and then solve this model the slow motion with a separate equation. Then we are splitting the previous equation in two subsystems, one modeling the fast motions and another modeling the slow motions. So by doing so, and to obtain that fast motion, we sum up the previous layer equation. For each layer, we sum all the equation over all the layers to form this equation. So basically, we have the same terms like in previous one, but we sum all the layers to have this one single set of equation. And everything looks the same, like I said, to obtain these terms in that version term, we have to sum all the terms in the layer equation to have those terms. And the same thing goes for the viscosity term. Okay. So now we we split the system into two, the fast motion and then the slow motion. And but nothing said that if we split that, then we entirely split all the variables. But those variables still contain some external gravity wave or external fast motion. So the idea is also to split those dependent variables in the previous, like the mass variables, the momentum variables. So we start by saying that, and the reason that if due to the presence of those external gravity waves, by just looking at the surface of the ocean, we can predict the behavior of the mass field. And the same thing goes if we take that big chunk of ocean, we can assume that the velocity is almost linear independent of the depth. So using those assumptions, we split this dependent variables. The PD is just the pressure for the barotropic, like the amount, the entire system. And this represents the pressure in each layers. And the velocity UK represents the velocity in each layers, and the U bar here represents the velocity for the entire system. So we split that variable into two, and where that here represents the perturbation in the initial pressure over time. Right. So now with these splitting variables, we have this way. We have to rewrite our previous equation with these splitting variables, or we do something else. So what we did is to rewrite the barotropic the one layer equation with the splitting variables. So we still have the conservation of the mass, which is good. That's what we want to have. And also, we also rewrite the momentum equation using the splitting variables. So we have to replace this UK delta PQ with the splitting variables that we all I just showed the previous slide. Putting that here is really messy, so I didn't put it there, but that's what we did. We rewrite the previous equation with the splitting variables. So the question now is, do you have to do the same thing for the layers, all the layers? So doing that is much complex. So what we decide is not to do so. So it is possible to do it. There's nothing wrong with doing that, but it's just like way complex to do so. So we decide to not to go there and do it differently. So why do we decide not to do that? Because the splitting variables from those previous ones, they are not necessarily exact. They still have some error in those splittings. So considering rewriting everything, those splitting variables is quite complex, and can cause some severe restriction to our numerical schemes. And then we also know that those splitting variables may still contain some external gravity, some external mode, like the one we are taking away from. They can still contain some. So the idea is, okay, let's go back and solve our original layers equations. But at each terms, at the end of each term step, what we are going to do, we are going to reconcile the barotropic systems and the baroclinic systems, like the big ocean equation and then the small layer equation. And one thing I also want to mention is that those systems, they are not independent from each other. To obtain the barotropic equation, we sum up the layers equation. So at each term step, they have to be like consistent with each other. Otherwise, we will have a big problem. So we have now our equation. We have everything, but how do we solve them numerically? Because we don't have exact solution. So that's why we use the nodal digit distribution method, and where we have, for instance, the idea those this brief summary of the digit method. If you have a domain, we divide those domains into different places, and in our terminology we call them elements. So each element we place a different briefness in that domain, depending on the polynomial order. So here I'm just showing the example of 4 order polynomial. So that's why we have like 1, 2, no, 3. That's in that we have 3. 1, 2, 3, 4. 3 order polynomial. Then the basic function we are using that polynomial because of another space. And in the basic combination, we have to expand the dependent variables with basically a linear combination with this function. And these are the Lagrange basis function and also Lagrange polynomial. And this QG represent the value of this variable at these 3 points. So that's how we obtain the solution in each element. So basically, we compute the solution on each element level and then combine them to form the global solution in our entire domain. Okay. So now we have to use that. I'm going to use that idea, to solve our previous equation. So, like I said, those previous equations are so complex. So I'm just presenting only the momentum equation for the layer equation. And the reason why I show this one is because there's something coming here, and we need to know how to solve it or how to compute that. And in order to apply the DD, we need to write the weak formulation of this, the previous equation. And we interpret the previous equation with the test function and then interpret that. And doing integration by part of this term, we have this term. And this is the integral at the edges of this element. So we have to compute the flux. We have to compute the value at this element edges. So that's why that's this integral comes in. So, and how we have this, and then we can rewrite this integral by replacing these quantities with their polynomial expansion. That's how we write the TD formulation. But I skipped that because it's way putting that on slide is going to be so much mathematics. So now the question: how do we now compute the flattics? That's when flat means the value at element edges. How do we compute that? So since we have two systems, we have to compute for both systems, for the barotropic system and also for the barotropic system. So since we are considering the whole ocean or the whole fluid domain for the barotropic, we assume that the variation will be almost linear, like in terms of. So we assume in a very small terms that we can assume that the system is near linear. So we linearize the barotropic equation and then solve the Riemann problem at those element edges. So basically, by doing that, we obtain these two flux population. And then this one, by looking at this, those who are familiar with this, like last Friedrich flux for the both system. And where this is the total of the fluid when the fluid is at initial state. And then, how do we do for the barotrapic? Do you have to do the same thing? Doing this for the barotrapic is going to be complex because you have to linearize all these layers equation. So doing that is complex. So we decided not to do that, and what we did is just to apply the standard flux. So if we compare these two elements, we are sharing this. They have to communicate their information between these edges and this edge. So what we did, to pick this value, the value at these edges, and the value at this edge, and take the average of them, and let's compute the flux. Yeah. Now, we have a deed, then we need to advance the model in time. So to do that, we use the time integration method to construct the prediction and the correction steps. And this time is quite simpler, where we use the Euler method to advance the solution in time. And for the prediction, we predict the barotrapic variables, and predict the barotrapic variables are all those developing for those points in the element. And then we do the same thing. After the prediction step, we have to correct it. So the correction step using the average from the previous step and the correction and the prediction step in order to correct the barotropic and the barotrapic quantities. So here we have this idea, like where we have the barotropic system, and then we have the layers equation. And for one big long barotrapic or the layers equation, for one, we have a sub-steps for the barotropic system. So if you take like between T and T plus T, Tn and T plus N plus 1, you have to divide it into small interval for the barotropic equations. Like I said, since we are solving the original equation for the layers, we have to reconcile the two systems at the end of each term steps. And that being said, that's why this is how we enforce the consistency. We assume that the summation over the layers pressure has to be equal to the pressure of the barotropic, and the summation over the layers of the momentum values in each layers have to be equal to the momentum for the paratropic equation. So this out then, in order to avoid any inconsistency between the two systems, we take the difference and then distribute the difference between these two quantities over the layers. And we take the difference between these two because they may not be necessarily equal to. So if they're not equal, then we take the difference between the two variables, those two quantities, and then distribute over the layers. Okay. So that's how we have the model built from the mathematical development to the numeric and to term integration. Then we implement this in NUMO. NUMO is the framework portion model using TG, and where we have this a single test case to verify if whatever we said so far makes sense or is actually correct. So we consider a free domain of 2 kilometers by 2 kilometers where we have the depth of each layer is 20 meters, and we run this for 4 hours. So you can see in the initial stage, we have a bump in the middle here, where we have that bump, where the equation description, and then we can see that as the time goes on, the flow that the fluid goes and bounces, and the wave goes and bounces back. And we can see the fast motion that I mentioned before. By just looking at the surface of the ocean, we can see the behavior of the mass wave. So we can see the fast motion on the top layer. So that's that, okay, we are observing all the dynamical features we expect to see. And unfortunately, we don't have an exact solution for this system. But what we did is to compare our numerical performance with some previous existing code or models that we know. The HICOM model is the US Navy model that we are trying to compare our model with. And also we have this HICOM my collaborator. We have brought a paper on this similar work in 2015, where he used only polynomial order 2 to verify these numerics. And so if you say this is the final volume of method, so we don't have elements, so we don't have like 40 in like a grid cell is 40 in the domain. And then if you will multiply these two by 20, it's like you have 40, so it's almost the same resolution. So we have for the DT, we have a very long, the idea of using that technique is to be able to use long-term step and use a very small term step for the control. So we have up to 180 and 8.5 for the small step for the whole system. And then we can see that we have a CFF condition of almost 101.8. So similarly, we are trying to compare our model with this reference one. And we can see that as we pick the same, if we pick the same configuration of parameters, we are having the same thing like in the previous one. And this one, the numeric is a bit different because we're using the modal DT and we are using the nodal DT. And then in our combination, we can use different polynomial order. We are not limited to 2, but we can use a different polynomial order. And as we increase the polynomial order, we can also see that we are decreasing the term step as we started DT. As the polynomial goes, we have to decrease that. The next one is to see if we can resolve a large scale simulation to see. And this one we contact 2,000 kilometers, the size of Atlantic Ocean, something else, where we have a wind blowing from the west to the east, and then the lower blowing there, and this in the southern part of the land. So due to the time constraint, I'm going to just show you the animation from this, where this simulation ran for 10 years. So around for 10 years, this is where the behavior of the sea surface height as the time goes on. So we're running for 10 years, and this is the surface height, and this is the velocity fields in the U direction or the S direction. So as you can see, we can clearly see, sorry, the color I use here is not. So we can clearly see that the formation of all these dynamical features that we expect to see. And currently, that's why we are now and trying to compare this result with HICOM model or some previous numerical results. So, and also for one last figure before I move on, this is obtained from the HICOM model, the US Navy model. This one is a previous developed by my advisor, and this one is current my model. And this model does show that we have a difference, like kind of different, but we just tell you that we are resolving some more dynamical features in the system because compared to the previous one. So this model is more dynamic compared to the previous one.
What's on the axis that what are you showing us here?
So this is kinetic energy in the field. Next. So for the future work, we continue with this by doing some more work by implement some limiters in the code, and also contribute adding some weight and bias endpoint in case the layers thickness is almost zero, and also run some performance tests to see how fast we are compared to PyCon or some other models. All right, thank you so much.
What, when you mentioned gravity waves, what are you talking about there?
What?
The first couple of slides.
Yes, when I right here, somewhere here. So
External gravity.
when I say external gravity waves, I mean that when we consider the layer or the layers, right? They either they get taken or tiny at the same proportion at a given time. So that forces that balance that. That's why we call it gravity waves. Okay. Yeah.
Gravity wave is motion that affects the entire column of water equally, right? And then that's what we'll call the external mode, right? It's like tsunami is that, right? Because it's like a column of water in which it moves up, and then all energy kind of travels equally throughout the column of water. But then the internal waves he's talking about, baroclinic waves, is those things that are there because we have differences in densities. Therefore, there's some motion which is not equally distributed throughout the whole column, right? It's like localized between the waves.
Okay, that's the term they use in the field of gravity waves.
Yes.
Okay.
Yeah, I like your presentation. However, like from the topic for me, it's a bit overwhelming because I don't really know what's happening. So it's like it's a lot.
Yeah.
I'd just like to know in simpler terms what it means by what you mean by barotropic and baroclinics.
So
just like a simple.
okay, when we say barotropic, we're talking about the fast motion. We are referring to the fast motion in the ocean. So those are due to the external gravity wave, meaning that when the for instance electrocontact tsunami, when the tsunami happened, all this happened so fast, so that if you consider water column can either go tiny or getting thickened or tiny at the same time, at approximately the same way. So that's what we call it gravity. So the barotropic, the baroclinic are the internal forces that happen within each water column. Yes.
Mathematically speaking, basically what it means is that there's an ocean, there's waves in the ocean, right? Mathematically, with the equations, you can decompose the solution, if you had one, into waves of different speed, right? Some are very fast, some are very slow. So he's basically trying to say that those barotropic waves are the external waves, the gravity waves, which travel really fast and affect everything, the entire water column. And then there exist other things which we saw, and we call them baroclinic. They are not the fast waves, right? That's gravity.
And then in your slides, you have mentioned there's a part where I think it's like change in density. Is it got to, I don't know, like the density of what is it got to the density of gravity? Your first slide. It must be the third or second slide. I'm not.
This one?
Yes.
Okay.
Yes, I don't understand that part. Oh, it's pressure, not density.
This is pressure. The kind of the ground or the derivative of the pressure.
The pressure or?
The pressure of the water column.
Okay.
Yes, is equal to like this is the rho is the density, and this is the gravity, like gravitational force.
Okay, so there are no, I know the ocean usually also has other materials, like you've explained, yeah. So then there's also density from those materials that's also affecting the ocean circulation, right? So did you consider that aspect in your research?
Well, we've not considered that, but when we talk about the density, we talk about the density of the water, including if you take the water column, right? But the density of that water, that's what we are considering. So we don't look at like the chemical, organic, like, everybody look at it. And it just the density of the water.
So again, that means a little bit, right? So there's an assumption, it simplifies it. And what it means, I guess, here is he's saying that you're gonna say that how pressure is changing only depends on how much water is above a certain point, which is close enough. There's other components in the non-hazarding model where you can say, oh, but there's also some other pressure effects which cause some like rapid changes, but it's not the case typically in the ocean, right? So I guess what you're asking is that the density depends on other things like salt in the ocean, I think is that what you're saying?
Just material usually the ocean has different types of material.
Okay. So what we worry about is salt because that affects density the most, right? And what the way he's addressing that is he's saying, let's imagine that if something is heavy, it's gonna go down, right? So you're gonna have heavy water, a layer of it here, then lighter and lighter, then lighter. It's another simplification, we see something like that, right? But it's close enough so that something gets useful conclusions from solving.
Then you also mentioned that this splitting method has some inconsistency. I think I missed that point. I missed your explanation for where the inconsistency are coming from.
Okay, so it's time. So what we can do, the inconsistency is coming from the fact that we are splitting. We are taking the two systems. We are pulling out. Let me put it on. We are pulling out the fast motion from the system. But pulling that doesn't mean that we remove everything completely from there. So there becomes some trace of those one inside the system after pulling them out. So that's what we call it. So we need to make sure that everything like connect to each other, like in the right way. Yes. All right. Thank you all.
Very well, I guess, the vast portion simulated, and we see what happens with each layer, and also a large scale motion simulator to see what happens with the column. But they might not give you the same answer.
So you solve two different equations, right? And you solve layered equations, then you solve those small steps, big equations.